The development of the jet engine stands as one of the most profound technological achievements of the modern era, a mechanical marvel that has fundamentally reshaped the boundaries of human connectivity, global commerce, and geopolitical strategy. At its core, a jet engine is a thermodynamic reaction power plant that operates on the Brayton cycle, discharging a high-velocity stream of compressed ignited gas to generate continuous thrust. To the general public, the engine hanging beneath the wing of a commercial airliner might appear as a simple roaring cylinder, but beneath that cowling lies a century of relentless innovation. From highly experimental, metallurgically limited prototypes forged in the shadow of global conflict to the hyper-efficient digitalized power plants of today, the jet engine represents the absolute pinnacle of material science, fluid dynamics, and mechanical engineering. Understanding the trajectory of this technology requires a journey through time, tracing how theoretical thermodynamic concepts evolved into the lifeblood of the modern global economy, and how the urgent mandate for environmental sustainability is currently driving the most radical redesigns in aviation history. The conceptual framework for jet propulsion actually predates the physical capability to construct such an engine. In 1908, the French engineer René Lorin patented an early concept for jet propulsion in which a reciprocating piston engine compressed fluid to generate thrust. By 1913, Lorin had further patented a supersonic ramjet engine that relied entirely on slowing down high-velocity airflow to subsonic speeds to achieve compression without moving parts. Following Lorin's early theoretical work, Maxime Guillaume patented the first concept for an axial-flow turbine engine in 1921. Guillaume's visionary design outlined a multi-stage compressor and turbine combined with a massive single combustion chamber, an architecture that closely mirrors the eventual design of modern jet engines. However, the transition from patents to practical power plants was stymied by the severe manufacturing and metallurgical limitations of the 1920s. The immense pressures and temperatures required for sustained jet propulsion simply melted the metals available at the time, and the necessary compressor efficiencies were deemed physically unattainable by contemporary institutions. The breakthrough that transformed theoretical physics into operational reality was achieved through the parallel yet strictly independent efforts of a British Royal Air Force officer named Frank Whittle and a German physicist named Hans von Ohain. In 1928, as a cadet at the Royal Air Force College, Cranwell, Whittle formally submitted his concepts for a turbojet to his superiors, eventually securing a British patent in 1932. Whittle's engine utilized a centrifugal compressor and turbine, a design where incoming air was drawn near the axis, flung outward to the periphery by centrifugal force to achieve rapid compression, and then returned to the axis through carefully engineered ducts. Completely unaware of Whittle's progress across the English Channel, Hans von Ohain was writing his university thesis on jet propulsion and secured a German patent in 1936. Von Ohain's initial design uniquely combined a centrifugal compressor with a centrifugal radial turbine, an architecture that maintained the gas direction relatively aligned with the engine axis, but was ultimately deemed an evolutionary dead end, as purely centrifugal turbine jet engines proved impractical for future scaling. Translating these pioneering patents into functional machines required overcoming immense technical hurdles, particularly the challenge of designing combustion chambers that could sustain continuous ignition without instantly vaporizing the surrounding turbine stages. Despite these formidable obstacles, von Ohain's collaboration with the prominent German aircraft manufacturer Ernst Heinkel culminated in the world's first successful turbojet-powered flight. On August 27, 1939, just days before the outbreak of World War II, the Heinkel HE-178 took to the skies powered by von Ohain's HES-3B engine. Britain quickly followed suit, Whittle's W1 engine, developed through his startup enterprise Powerjets Limited, successfully powered the Gloster E-28-39 on its maiden flight on April 12, 1941. As the global conflict rapidly intensified, the strategic necessity for high-altitude, high-speed interceptors catalyzed the operational deployment of these highly experimental technologies. By 1943, Germany had transitioned from von Ohain's centrifugal designs to more streamlined axial-flow compressors, producing the Junkers J004, which powered the feared Messerschmitt Me-262. The Me-262 offered unprecedented speed and altitude capabilities, providing a terrifying glimpse into the future of aerial combat and instantly rendering propeller-driven fighters obsolete. Simultaneously, Britain deployed the Gloster Meteor, an interceptor powered by Rolls-Royce Welland engines that were derived directly from Whittle's centrifugal architecture. While the jet engine arrived too late to unilaterally alter the outcome of World War II, its combat debut irreversibly shifted the paradigm of aviation and set the stage for the intense technological arms race of the Cold War. The immediate post-war period was defined by a critical mechanical reckoning regarding how air should be compressed within the engine. Early British and American jet engines relied heavily on centrifugal compressors due to their mechanical simplicity, robustness, and ability to achieve a high compression ratio in a single stage. However, centrifugal compressors required the incoming air to negotiate two 90-degree turns, and the massive rotating impeller mandated a disproportionately large engine diameter. This massive frontal area resulted in severe aerodynamic drag, rendering the centrifugal turbojet structurally unsuitable for the supersonic speeds demanded by Cold War military strategists. Consequently, the global aerospace industry decisively shifted towards the axial-flow compressor, a technology initially pioneered by German engineers during the war. In an axial compressor, the working fluid flows continuously parallel to the axis of rotation, passing through alternating rows of rotating airfoils called rotors that accelerate the air and stationary airfoils called stators that diffuse the air to convert kinetic energy into a pressure increase. While a single axial stage produces a relatively low pressure increase of 1.1 to 1.4 to 1, stacking multiple stages allows for an exceptionally high overall pressure ratio, culminating in a highly streamlined, narrow engine profile that minimizes drag and is ideal for high-speed flight. To push military aircraft beyond the sound barrier, aerospace engineers developed thrust augmentation systems known to the public as afterburners. The concept of afterburning involves injecting raw aviation fuel directly into the oxygen-rich, searingly hot exhaust stream aft of the turbine stages, creating a secondary combustion process that massively increases exhaust velocity and thrust. Early experimentation with this technology in the United States was pioneered by the National Advisory Committee for Aeronautics at the Lewis Flight Propulsion Laboratory in 1944, utilizing General Electric's early turbojets. By the late 1940s and early 1950s, aerospace contractors like Ryan Aeronautical Company and Pratt & Whitney had perfected the eyelid variable exhaust nozzle, an intricate mechanical innovation required to manage the massive fluctuations in exhaust pressure generated by the afterburner on engines like the J47 and J57. This technology became standard for military interceptors, enabling supersonic dashes and vertical climbs at the cost of catastrophic fuel consumption. As military aviation breached Mach 1, commercial aviation sought to adapt the turbojet to conquer intercontinental distances, ushering in the commercial jet age. The British achieved the first major milestone with the de Havilland DH-106 Comet, which entered commercial service in 1952. featuring an aerodynamically clean design with Ford to Havilland Ghost turbojets buried invisibly inside the wing roots, a fully pressurized cabin, and cruising altitudes far above turbulent weather disturbances. The Comet initially promised a revolution in passenger comfort and speed. Tragically, the limits of mid-century material science and structural engineering soon surfaced. Within a year of its debut, a series of fatal mid-flight catastrophic airframe failures grounded the entire fleet. Extensive metallurgical testing revealed that repeated stress of pressurization and depressurization cycles at high altitudes had induced severe metal fatigue, a phenomenon heavily exacerbated by stress concentrations around the Comet's aesthetic square-cut windows and automatic direction finder antenna cutouts. Rival manufacturers rapidly absorbed the painful engineering lessons of the Comet tragedy. In the United States, Boeing developed the 367-80 prototype, which quickly evolved into the iconic Boeing 707. Entering service with Pan American World Airways in 1958, the 707 featured swept wings and 4 Pratt & Whitney JT3C turbojets mounted in discrete pods slung beneath the wings. This podded design, adapted from the military B-47 bomber, isolated the engines from the passenger cabin, localized any potential uncontained engine failures, and drastically reduced structural stress on the wing roots. The Boeing 707 was vastly larger, faster, and more reliable than its piston engine predecessors, cutting transatlantic travel times in half and effectively cementing American dominance in the early era of global commercial jet manufacture. Despite their revolutionary speed, early commercial turbojets were staggeringly loud and highly inefficient for subsonic cruise. Aerospace engineers realized that overall engine efficiency is the product of thermal efficiency, which is determined by the pressure ratio and turbine inlet temperature, and propulsive efficiency, which is the ratio of useful thrust power to the kinetic energy left swirling in the engine's wake. A pure turbojet generates thrust by expelling a relatively small mass of air at extremely high velocity, which results in a poor propulsive efficiency at subsonic speeds and devastating noise pollution that shattered the quiet of communities surrounding early airports. The brilliant engineering solution to this thermodynamic dilemma was the turbofan engine. By adding a remarkably large fan at the front of the compressor, driven by an additional turbine stage at the rear of the engine, a significant portion of the incoming air bypasses the engine's combustion core entirely, flowing around it to generate thrust. The ratio of this bypassed air to the air entering the core is known as the bypass ratio. In 1960, Rolls-Royce introduced the Conway, the first turbofan designed specifically for commercial aircraft, featuring a modest bypass ratio of 0.3 to 1. By moving a much larger mass of air at a slower velocity, the turbofan radically improved propulsive efficiency, drastically reduced fuel consumption, and significantly dampened the shearing noise of the high-velocity core exhaust. This thermodynamic principle established the engineering baseline for every subsequent commercial airliner engine constructed to this day. The relentless pursuit of even higher thermal efficiencies over the past 40 years has driven an absolute reliance on advanced material science, moving the industry from mechanical innovation into the realm of atomic manipulation. Because thermal efficiency scales proportionally with the temperature difference across the combustion cycle, engineers are constantly pushed to operate turbine inlet temperatures as hot as structurally possible. Modern jet engines rely heavily on titanium alloys in the front, cold sections of the engine, such as the massive fan and low-pressure compressor. Titanium provides an exceptional strength-to-weight ratio and superb corrosion resistance, making it ideal for ingesting bird strikes and debris, yet it suffers from severe metallurgical limitations at extreme temperatures and cannot be utilized near the combustion chamber. Consequently, the hot sections of the engine, the combustor and the high-pressure turbine, are constructed from incredibly advanced nickel-based superalloys. Modern generations of these superalloys are heavily doped with refractory elements such as tantalum, tungsten, and rhenium, which drastically enhance their high-temperature mechanical properties, albeit at the expense of inherent oxidation resistance. Because modern turbine blades operate in environments where the surrounding gas temperature regularly exceeds the physical melting point of the base metal by several hundred degrees, raw metallurgy alone is insufficient to prevent catastrophic engine failure. To survive the inferno of the high-pressure turbine while enduring massive centrifugal forces from rotating at over 10,000 revolutions per minute, engineers revolutionized how metals are cast. Traditionally cast turbine blades are polycrystalline, meaning they comprise a microscopic three-dimensional mosaic of varying metal crystals or grains formed during solidification in the mold. Under extreme heat and continuous centrifugal stress, the boundaries between these microscopic grains become intensely vulnerable to a phenomenon known as creep deformation, where the metal slowly stretches, deforms, and eventually fails. Beginning in the later decades of the 20th century, aerospace companies perfected directional solidification and ultimately single crystal casting. By meticulously controlling the cooling process to entirely eliminate grain boundaries within the airfoil, single crystal blades exhibit up to 9 times the relative lifespan for creep strength and thermal fatigue resistance compared to their older polycrystalline counterparts. To further insulate these single crystal blades from the melting heat of the high-pressure turbine, the aerospace industry developed advanced thermal barrier coatings. These microscopic ceramic layers possess extraordinarily low thermal conductivity and are applied directly to the working surface of the turbine blades. Deposited onto the blade surfaces using techniques like electron beam physical vapor deposition, which provides superior strain tolerance through a flexible columnar microstructure, or air plasma spray, these coatings are mere a fraction of a millimeter thick. Yet when combined with intricate internal cooling passages that bleed cooler air from the compressor out through microscopic holes in the blade, these thermal barrier coatings create a vital temperature drop of 100 to 300 degrees Celsius between the volatile exhaust gas and the metal surface. Because these ceramic coatings are completely transparent to oxygen, an intermediate oxidation-resistant bond coat must first be applied to anchor the ceramic thermal blanket to the superalloy substrate. The amalgamation of these advanced materials allowed for unparalleled increases in overall pressure ratios and bypass dimensions, initiating the era of the modern ultra-high bypass turbofan. A definitive milestone in this modern era was the General Electric GE90, developed in the 1990s specifically to power the massive twin-engine Boeing 777. To achieve a remarkable 9-to-1 bypass ratio, General Electric replaced the traditionally heavy titanium fan blades with highly durable, incredibly lightweight carbon fiber blades. Manufactured by weaving thin sheets of carbon fibers and fusing them together with specialized resin in a process somewhat akin to layering pastry dough, these composite blades drastically reduced the overall engine weight by hundreds of pounds and permitted unprecedentedly large fan diameters. Certified in 1995 in a tense room of Federal Aviation officials, the GE90 later set a world record by producing 127,900 pounds of sustained thrust, and it famously became the first commercial jet engine to utilize a 3D printed component, an additive manufacturing breakthrough that solved critical ice buildup issues on internal sensors. Similar paradigm shifts occurred across the Atlantic, with the Rolls-Royce Trent engine family routinely achieving bypass ratios of 10-to-1, making them 70% more fuel efficient than early turbofans like the Conway. This modern era of physical manufacturing has been profoundly amplified by the digital revolution, specifically the integration of computer-aided design, computational fluid dynamics, and interconnected data paradigms. Traditional test-to-failure physical prototyping, where engineers built a physical engine and pushed it until it exploded, has largely been supplanted by the creation of digital twins. A digital twin is a high-fidelity virtual replica of a physical engine that continuously ingests real-time data from hundreds of interconnected sensors embedded in the operational aircraft. Monitoring incredibly minute variables such as vibration frequency, internal pressures, and exhaust gas temperatures, the digital twin dynamically updates its virtual parameters to mirror the precise physical wear and tear experienced by the engine currently flying through the sky. This seamless connectivity enables predictive maintenance, allowing ground crews to identify microscopic anomalies and replace components the moment a plane lands, long before the wear manifests as an operational failure. This digital foresight drastically minimizes costly aircraft downtime, enhances passenger safety, and effectively eliminates surprise mechanical faults that once plagued the industry. The macroeconomic ripple effects of the jet engine's technical maturation are staggering in their global breadth. The introduction of highly reliable, fuel-efficient wide-body aircraft like the Boeing 747 in 1970 severely compressed the economic cost of a seat mile, fundamentally democratizing long-distance travel. Air travel rapidly evolved from an exclusive luxury reserved for the wealthy elite into a ubiquitous mass transit utility. Between 1950 and 2020, passenger and freight traffic growth consistently outpaced gross world product growth, acting as a primary catalyst for globalized trade and proving that every unit of economic growth is inherently tied to aviation activity. The deregulation of the United States airline industry in 1978 further accelerated this transformation, allowing commercial carriers to set competitive airfares and establish sprawling, optimized route networks that made flying accessible to the middle class. Simultaneously, the sheer reliability and speed of the jet engine birthed the modern air express logistics industry. In 1973, Federal Express emerged as the first airline dedicated exclusively to overnight package delivery, fundamentally rewiring global supply chain expectations and altering the speed of international commerce. Today, the aviation sector stands as an unparalleled economic engine, directly and indirectly supporting an estimated 86.5 million jobs worldwide and generating a total global economic impact of $4.1 trillion, acting as the primary facilitator for 58% of all international tourism. The jet engine did not merely alter civilian life and commerce, it fundamentally rewrote the tactical doctrines of geopolitical military strategy and power projection. The exponential leap in speed and payload capacity rendered early propeller-driven heavy bombers obsolete almost overnight, prompting the development of the swept-wing Boeing B-47 Stratojet and subsequently the massive B-52 Stratofortress, which formed the airborne backbone of the United States' nuclear deterrence triad during the tense decades of the Cold War. Furthermore, the insatiable fuel consumption of early military turbojets necessitated the rapid maturation of in-flight aerial refueling techniques. By utilizing massive tanker aircraft like the KC-135, global superpowers achieved effectively infinite range capabilities, allowing fighter interceptors and heavy bombers to strike targets anywhere on the globe at a moment's notice, without reliance on vulnerable proximate land bases. The domestic capability to design and manufacture highly advanced jet engines remains a tightly guarded matter of national security, granting nations that possess this complex intellectual property significant strategic autonomy and leverage in unpredictable global dynamics. Perhaps the most significant regulatory and economic shift facilitated by the increasing reliability of modern turbofans is the advent of extended-range twin-engine operations standards, commonly known as ETOPS. In the early days of commercial aviation, twin-engine aircraft were strictly forbidden from flying routes that placed them more than 60 minutes away from an adequate diversion airport, a draconian safety measure intended to ensure survival in the event of an engine failure. This restriction forced airlines to rely on expensive, fuel-thirsty 3- and 4-engine aircraft for transoceanic flights over the Atlantic and Pacific. However, as the dispatch reliability of advanced engines like the GE90 and Pratt & Whitney PW4000 soared to unprecedented heights, aviation regulatory bodies began granting ETOPS extensions based on proven statistical safety. Starting with 120-minute authorizations in the 1980s for the Boeing 767, standards evolved to 180 minutes and eventually extended beyond 200 minutes for heavily verified airframes like the Boeing 777. ETOPS fundamentally altered airline economics by rendering the 4-engine passenger jet largely obsolete, allowing carriers to pioneer direct, point-to-point international routing rather than relying solely on the congested traditional hub-and-spoke model. Due to the colossal capital investments, staggering research and development costs, and fierce regulatory hurdles associated with manufacturing these marvels of modern engineering, the aerospace engine industry has experienced intense, decades-long consolidation. Today, the global commercial engine market is dominated by the Big Three: GE Aerospace, Rolls-Royce, and Pratt & Whitney. These major manufacturers often form strategic joint ventures to pool immense financial risk and technical expertise in highly lucrative sectors, most notably CFM International, a massively successful 50-50 partnership between GE and France's Safran aircraft engines that dominates the single-aisle aircraft market. This engine manufacturing ecosystem represents an $81 billion industry as of 2024, characterized by massive barriers to entry and a robust secondary market centered around engine leasing and long-term, highly profitable maintenance contracts that keep these complex machines flying safely for decades. As the global aviation industry aggressively commits to a unified goal of achieving net zero carbon emissions by the year 2050, the aerospace sector is currently undergoing its most profound mechanical renaissance since the invention of the turbofan. In the immediate term, maximum fuel efficiency is being meticulously squeezed from traditional ducted architectures through the maturation of geared turbofan technology. In a traditional turbofan engine, the large front fan and the low-pressure turbine share a single continuous shaft, meaning both must rotate at the exact same speed. A geared architecture inserts a highly complex planetary power gearbox between the two components, allowing the front fan to spin at a slower, aerodynamically optimal speed to reduce noise and drag, while the turbine spins at a much faster, thermodynamically efficient speed. Rolls-Royce is currently validating this specific concept for the wide-body market through its UltraFan demonstrator program, which utilizes the world's largest aero engine testbed to deliver a 25% fuel efficiency leap over earlier Trent engines. Furthermore, the relentless drive for core efficiency has culminated in modern marvels like the General Electric GE9X, which features an astonishing overall pressure ratio of 60:1 and utilizes advanced ceramic matrix composites to endure internal temperatures while powering the massive Boeing 777X. Looking toward the second half of the 2030s, the physical limitations of traditional ducted engines are forcing a radical paradigm shift in propulsion architecture. As engineers attempt to increase the bypass ratio even further to improve propulsive efficiency, the physical diameter of the engine nacelle, which is the aerodynamic outer casing, must proportionately increase. Eventually, the aerodynamic drag and immense weight of a gigantic protective nacelle entirely cancel out any efficiency gains provided by the larger fan. To circumvent this physical boundary, CFM International launched the Revolutionary Innovation for Sustainable Engines program. The absolute cornerstone of this ambitious program is the open fan, or unducted engine architecture. By completely stripping away the outer engine casing, engineers can mount massive, variable-pitch composite fan blades that spin freely in the open air, acting much like highly advanced propellers driven by a jet core. Supported by massive supercomputing resources capable of modeling incredibly complex acoustic physics, the open fan is designed to achieve an unprecedented bypass ratio of 60:1, yielding a 20% reduction in fuel consumption and emissions, while strictly maintaining the flight speed and cabin noise levels of conventional ducted turbofans. Parallel to these radical mechanical redesigns, the industry is aggressively investing in altering the fundamental thermodynamic chemistry of flight through alternative energy sources. Sustainable aviation fuels are bio-based or synthetic e-fuels produced from captured atmospheric carbon dioxide, municipal waste, or agricultural biomass. Because these fuels essentially recycle carbon that was recently extracted from the atmosphere through plant growth or direct air capture, their life cycle carbon footprint is up to 80% lower than traditional fossil-derived kerosene. Critically, sustainable aviation fuels act as a drop-in energy source, meaning they require zero mechanical modifications to existing engine infrastructure or airport refueling pipelines. Major engine manufacturers have ensured that all next-generation testing, including the revolutionary CFM Open Fan and Rolls-Royce UltraFan programs, operates with 100% compatibility for these sustainable fuels. For a truly zero-emission future, engineers are intensely exploring the volatile complexities of hydrogen propulsion. Hydrogen is an exceptionally attractive fuel due to its incredibly high specific energy and total lack of carbon emissions upon combustion. However, its volumetric energy density is notoriously poor compared to standard aviation fuel, necessitating massively expanded, heavily insulated cryogenic storage tanks to keep the hydrogen in a liquid state. These massive tanks do not easily integrate into the traditional tube and wing aircraft designs that have dominated aviation for a century. While ambitious startups are actively retrofitting small, short-haul commuter aircraft to run on hydrogen fuel cells, integrating hydrogen combustion directly into massive wide-body jet engines remains a monumental material and aerodynamic challenge, a hurdle likely requiring a transition to radically new blended wing-body aircraft geometries in the 2040s. The final frontier of aerospace propulsion lies in electrification, a domain currently constrained by the rigid laws of physics. While the terrestrial automotive industry has successfully transitioned to lithium-ion batteries, aviation is handcuffed by gravity and specific energy density. Traditional jet fuel boasts an energy density of approximately 12,000 watt-hours per kilogram, a figure currently vastly superior to even the most advanced lithium-ion and lithium-sulfur batteries. Because an aircraft must physically lift its fuel source off the ground, a purely battery-electric aircraft the size of a standard commercial jetliner would be overwhelmingly crippled by battery weight, heavily restricting its range to a fraction of a fossil fuel counterpart and leaving virtually no weight capacity for paying passengers. Furthermore, unlike liquid jet fuel, which burns off during flight and leaves the aircraft significantly lighter for a safe landing, dead batteries retain their massive full weight throughout the entirety of the flight cycle. Consequently, research institutions and aerospace firms are pivoting heavily toward hybrid electric propulsion systems as a viable stepping stone. NASA's SCEPTR program and the experimental X-57 Maxwell have demonstrated the viability of distributed electric propulsion on light aircraft, using small electric motors spread across the wing to optimize aerodynamic lift and reduce drag. While for the commercial transport sector, concepts such as the Boeing Sugar Volt, standing for Subsonic Ultra-Green Aircraft Research, envision passenger aircraft utilizing a traditional gas turbine engine augmented by a powerful battery system during highly demanding phases of flight, such as takeoff and initial climb. By load-sharing the intense power requirements, the gas turbine can be significantly downsized and optimized strictly for high-altitude cruise efficiency, potentially yielding total fuel burn reductions of nearly 30%. As electrical energy storage slowly matures over the next century, these complex hybrid systems are projected to enter the regional aviation market, serving as the crucial technological bridge between our century of fossil fuel dependency and the ultimate dream of fully electrified, silent, and sustainable flight.